All right, let's get going here. Where's my thing? Mode. Get big. Okay, so before we get talking about multivariate probability today, were there any questions from Tuesday about linear algebra, matrix algebra, stuff like that? So we're going to be using the stuff that we talked about on Tuesday a lot today. Okay, so as usual, Columbia University employee, Columbia develops STAN, use STAN for business purposes. That creates the appearance of a conflict of interest, even though today we're not specifically talking very much about STAN. We're just talking about probability in the sort of abstract sense before we get into any sort of estimation. So lots of good math today, but not really very much code. And, you know, we'll pick up using this stuff, particularly the multivariate normal distribution next week when we start talking about doing hierarchical models using RStan-ARM, and those are going to have a multivariate normal prior on some of the parameters in the model. So we need to get familiar with multivariate probability in general, multivariate normal distribution in particular, it being undoubtedly the most important of the multivariate distributions. So usually when we're talking about multivariate probability distributions, we're talking about a probability distribution for a vector of continuous random variables. Now, we didn't really specifically address that much the case of a vector of integer random variables. We did a little bit on Tuesday, talking about the categorical distribution, talking about the multinomial distribution, and those were not actually too difficult if you understood the stuff that we talked about the first few weeks of the semester on you know, probability mass functions and other things dealing with discrete random variables, the collection of them into you know, integers in the case of a multinomial distribution, or the 0, 0, 0, and then one of them is a 1 in the categorical distribution. Not too hard to understand. Of course, the categorical and the multinomial distribution have a parameter, which is a simplex, a vector of continuous real numbers that are non-negative and add up to 1. So you have to understand a little bit about vectors, but you can certainly write the probability mass function for a categorical random variable or a multinomial random variable using only scalar algebra. But just in the same way that univariate probability for continuous random variables is a bit harder, a bit more calculus intensive than probability in the univariate case for a discrete random variable, probability in the multivariate case, particularly when we are thinking in particular about distributions for vectors of continuous random variables, is a bit harder still, a bit more, I guess, intensive in some ways on the calculus. And that's why we forestalled this for about as long as we could. But if you want to get into talking about hierarchical models, which we'll do next week, if you really want to understand the frequentist perspective on sampling distributions of estimators for a bunch of parameters in the same model, you got to know some stuff about multivariate probability, and especially the multivariate normal distribution. But in general, if X is a random vector, it has size k, it's considered to be continuous, so it lives in the real numbers in k dimensions. That would be its sample space omega, or some subset of the real numbers in k dimensions. So we could have the restriction that X is all positive or something like that. But in general, we don't need to. We can define the CDF of the random variable X as the probability that the first random variable x1, that's big X1, is less than or equal to some given value x1, and simultaneously the random variable big X2 is less than or equal to some given value little x2, and simultaneously the kth random variable big xk is less than or equal to some given value little xk. And so that is a conceptually easy enough thing to understand, the probability that all k of these conditions are true simultaneously. And since they're all less than or equal, we have, you know, a fairly easy generalization of our idea that we had before of a univariate CDF. What's the probability that random variable is less than or equal to some value from its sample space? Now we can generalize that to the case of k random variables taken or considered together. So if that is the CDF, big F, probability of all these things holding simultaneously, we can define the PDF of a distribution as what's known as the total derivative of the CDF. And the total derivative of the CDF is obtained by taking the CDF and differentiating it with respect to x1. That will yield a new function of x. We take that new function of x, differentiate it with respect to x2, we get a new function, another new function. We take that another new function, differentiate it with respect to x3, et cetera, until we get to the end and we're differentiating some function with respect to the kth value in the random vector x. And now we're down to a scalar function of a vector, and that scalar function of the vector is little f, or the PDF of random variable x who has some distribution that is characterized by this CDF and this PDF. Now, these are mostly just conceptual things, and especially with multivariate distributions, we're almost never able to write down the CDF in any sort of an explicit form in order to differentiate it explicitly. Conversely, we're not able to take, you know, some non-negative function, we'll call it a kernel function, and integrate it in k dimensions to, you know, show that the integral is finite, and then we can divide by whatever that is, and now it integrates to 1 over all k dimensions. Almost never are we going to be able to do that explicitly in the multivariate case. Sometimes we can do it in the univariate case, and, you know, applications are dominated by situations where we can, you know, the univariate normal distribution, in a manner of speaking, logistic distribution, things like that. But conceptually, we have a CDF that is reasonably easy to understand. Conceptually, we have a PDF that is the total derivative of the CDF. Rashika. Oh, yeah. I haven't gotten to that one yet. Becca?
So in the CDF, do those values of x1, x2, etc., like, they are all increasing, right? Like,
no, x2 can be less than x1. Big X2 can be less than big X1.
Little x, the value that you like.
Oh, these?
Yeah.
Again, it's just saying, is the first random variable in the first position of the vector less than or equal to some number? And right. Then is the second random variable in the second position less than or equal to some number? It doesn't have anything to do with the relative sizes of those two random variables.
So you have a CDF for every combination of x1 and x. Right.
Now, most of the distributions that we're going to deal with, their CDF and their PDF are going to be invariant to a reordering, a permutation of the elements in the vector. But maybe in some cases we want to put an additional restriction on the sample space of x, that, you know, x1 has to be less than x2, has to be less than x3, has to be less. But that's just chopping off a big chunk of the sample space, not something that is logically true about multivariate random variables in general. Other questions about that so far before I get into what Rashika was asking about? Okay, so if we can't do very much explicit calculus on, you know, a PDF or a CDF, how might we construct a multivariate distribution? And one way of doing so, which is reasonably common, is to write a multivariate PDF as using the general multiplication rule as the product of a marginal PDF for the first random variable multiplied by a conditional PDF for the second random variable given the first random variable multiplied by a conditional PDF for the third random variable given the first random variable and the second random variable, et cetera, multiplied by a conditional distribution for the last random variable given all the previous random variables. So in general, we can write that as a marginal distribution for the first random variable times the product of k minus 1 conditional PDFs, where each one of those PDFs is a conditional PDF for the little kth random variable given all the random variables that have come previously. This is sometimes called the telescopic form of a multivariate PDF. It's just, you know, one conditional on everything between it, and the first one, or everything before it, and the first one has nothing before it, so it's just a marginal PDF. This construction here, this product, yields a valid multivariate PDF, and you might be able to do some algebraic simplification of this to write it in the form of a joint vector rather than marginal times conditional times conditional times conditional, etc. Did that answer your question? Anyone else have a question about that? Jim.
So does the ordering matter then? Like it's random.
So in this case, yes, the ordering is, particularly with these, it's a particular conditional distribution for the kth given the first, the second, up to the k minus 1. So in that sense, the order does matter because the order determines what the conditional distributions are. But if you can, you know, multiply these all together, simplify it down, you may very well get a symmetric multivariate joint distribution, and the joint distribution could be, often is, invariant to a permutation of the elements. So one way of writing it down is like in this order, but if this holds, it's also true, I could write down this PDF equivalently by saying marginal PDF for the last one multiplied by conditional PDF of the next to last one given the last one, multiplied by conditional PDF of the second to last one given the next to last one and the last one, etc., all the way up till I get to the first one, and now I have conditional distribution of the first random variable given all the ones that come after it. Who is calling me? Maryland. Don't know anyone in Maryland. Questions about that? Please.
So basically, this is supposed to make it easier in some situations. So like if we know, for instance, it's easy for us to like take the derivative with respect to the first to x1. That's a situation where we would apply this, like, because it might be difficult to like actually analytically get like the whole thing at once.
It is analytically usually impossible to get the whole thing at once. And so this is one instance of breaking down a joint PDF into within reason manageable pieces. And that's one thing that we're going to see over and over again today, and the rest of the semester is that when you have some big joint multivariate thing, usually the best way to go about dealing with it is to decompose it into smaller parts. Really decompose it into the smallest parts you can. Not only is that going to make it easier for you to reason about and manipulate, but also it's often going to make it easier for Stan to sample from, you know, some multivariate distribution in an efficient fashion to get reasonable effective sample size and no, you know, warnings saying that this is not going well. So decompose, decompose, decompose. It is true that the CDF can be written as the multivariate integral of the PDF, integrating over the first random variable, then the second, blah, 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 up to the kth. That is, you know, usually impossible to do analytically, but just fundamental theorems of calculus ensure that that is true. Also true, but hard to do analytically in most cases, not totally all. But the expectation of some function g of a continuous random vector x is the integral over the whole sample space of the function multiplied by the PDF, integrated over the first variable, the second variable, etc. And so that is, you know, just a generalization of like the bivariate functions that we've taken the expectation of before. Now we have a k-dimensional integral rather than a two-dimensional integral, but conceptually this gives us the way to think about the expectation of some function of a continuous random vector. It is also true that the expectation of a vector is a vector of expectations. And so the expectation of some random vector x is going to be a vector which we could call mu, and it can be gotten at by filling, in this case, row vector with the expectation of x1, the expectation of x2, expectation of xk, although you have to do a bunch of integrals in order to obtain those things. But conceptually, the expectation of a vector is a vector of expectations, and the expectation of a matrix is a matrix of expectations. You know, everything of the same size. Also, we can think about the expectation of a particular g function, namely x minus mu, the vector, multiplied from the right by x minus mu transpose. So if x is of size k, its expectation mu will also be of size k. So we take a size k vector, subtract a size k vector, get another size k vector. This is a column vector, so it's going to be k by 1. And then we can multiply it on the right by a row vector, which is going to be 1 by k. These are conformable for multiplication and will yield a k by k matrix. This is the so-called outer product of a vector with itself. And the expectation of that k by k matrix that is composed by post-multiplying a column vector by a row vector is a special matrix. It has its own special Greek letter, capital sigma, which is a symmetric matrix, so it's equal to its own transpose. And it is a so-called variance covariance matrix, sometimes called a variance matrix, sometimes called a covariance matrix. 3 names for the same matrix, which is a k by k symmetric matrix that has the marginal variance of the kth variable along its diagonal. In the off-diagonal elements, it contains the covariance, in this case, between the first and second variable. But the covariance between the first and second variable is the same as the covariance between the second variable and the first variable. Consequently, these 2 elements of the matrix are equal. Indeed, every off-diagonal element of the matrix over here is equal to the corresponding element below the diagonal if I just switch the row index and the column indices, and that's what defines a symmetric matrix, in this case one that contains variances along the diagonal, covariances in each triangle. They're symmetric, and consequently that is why this sigma is called a variance covariance matrix or a variance matrix or a covariance matrix. Questions about sigma or mu or expectations of functions of random variables? So all of this simplifies to the case, well, what if k is 1? We have a vector of length 1, which we would ordinarily call a scalar. But in that case, you know, all this goes away, and we just have the variance of the first and the only random variable. Similarly with mu, that could just be a vector of size 1. Rashika?
So the variance part, so it's x minus mu. X itself is your has multiple variables, right? So
It's a vector.
It's a vector.
Like this, column vector. And subtract its expectation, also a column vector, multiplied by a row vector, you get k by k. That's a matrix. You can take the expectation of a k by k matrix, and you get a k by k matrix of expectations, which these variances and these covariances are for a particular g function. Okay. So to just sort of break it down to the two-dimensional case, recall, and I think we've said this before, that if we define the g function as just x minus its expectation multiplied by x2 minus its expectation, and we integrate this over both dimensions, weighting by the bivariate PDF, we get the covariance between x1 and x2, denoted little sigma 1, 2. And if we divide little sigma 1, 2 by the respective standard deviations, we get the correlation between the first two variables. That's unitless, constrained to the -1 to 1 interval. And the correlation is a unit-free measure of linear dependence, whereas the covariance is in the same units as x1 and x2. Also a measure of linear dependence, but one that is embedded depending on the units of those two variables. And so a lot of things in social sciences have essentially arbitrary units, and so there's some preference to use correlation as a general measure of linear dependence, so you don't have to worry about whether you're talking about, you know, pounds or kilograms or dollars or euros or anything like that. So if we have a variance covariance matrix sigma, that's k by k, we can define a k by k correlation matrix lambda that contains in its off-diagonal elements the correlation between variable I and variable j. Down the diagonal of lambda, we just have 1, 1, 1, 1, 1, 1. But in the off-diagonal elements, we have a bunch of correlations. As we said before, since the covariance between variables I and j is equal to the covariance between j and I, sigma is going to be a symmetric matrix. Along the diagonal, covariance of a variable with itself is really just a variance, and so we have variances along the diagonal, and that's where the name variance covariance matrix comes from. But we can write sigma as the product of three matrices, one of which is the same. So if we let delta be a diagonal matrix that has the standard deviation of the ith variable in the ith place along the diagonal, we can write a variance covariance matrix as the product of this diagonal matrix of standard deviations delta multiplied by our correlation matrix lambda, multiplied again on the right by our diagonal matrix of standard deviations. Recall that when we multiply a diagonal matrix such as delta by, you know, some other matrix on the right, that takes each row of the matrix on the right and bumps it up by the corresponding diagonal element of delta, which in this case is standard deviation. And then when we multiply a matrix by a diagonal matrix on the right, that scales up each row of the each column of the matrix on the right by the corresponding diagonal elements. So as a result, sigma is going to have in each of its off-diagonal elements some correlation multiplied by the standard deviation of the ith variable multiplied by the standard deviation of the jth variable, yielding a covariance. And along the diagonal of sigma, we're going to have the diagonal of lambda, which is just 1, multiplied by some standard deviation of the ith variable multiplied by the standard deviation of the ith variable again, which yields the variance of the ith variable multiplied by 1, or just the variance. So just the same way we were talking about a minute ago, decompose, decompose, decompose. One thing that's going to make it easier for you to deal with covariance matrices is to decompose them into a correlation matrix and a diagonal matrix of standard deviations. The diagonal matrix of standard deviations and the correlation matrix are each easier to deal with separately than their combined product, yielding a covariance matrix, which is actually kind of hard to deal with when we get into STAN, unless we use this composition of them. Questions? Decompose, decompose, decompose. Okay, so a little bit of practice from what we did toward the first part of the semester. If a scalar random variable z has a gamma distribution and consequently it has the following PDF, and x is a function of z, namely the reciprocal of z, what is the PDF of the random variable x? Or how do we go about figuring out what the PDF of the random variable x is? Salif.
Remember, well, we can, I think the first step is to express it, whether or not.
And so how would we express z as a function of x?
Take times z by x, so z equals.
Yes, it does.
Then we take the derivative with respect to x.
Okay, so we take the derivative of z with respect to x. We're going to need that. So what is the derivative of z with respect to x?
Root of plus. Oh, yeah.
Okay. Negative 1 over x squared. We're going to need that. Okay, what else we need to do?
Multiply with something. We need to multiply with something.
Multiply something.
Yes.
Well, we've only got one thing so far. What are we going to multiply the derivative of z with respect to x by? And multiply it by the PDF of z written as a function of x. So just to go through the logic of this again, you know, z is going to have some CDF, and since we know the PDF in principle, we know what the corresponding CDF is. So the probability that z, the variable we start with the gamma distribution, is less than or equal to some value little z is the CDF of z. Consequently, the probability the random variable x is less than or equal to some value little x, which could be a function of z, before we were considering the case of increasing transformations like e or log or something like that. In this case, we have a monotonically decreasing transformation. The bigger is z, the smaller is x in magnitude, and vice versa. And so the probability, and that flips the signs around. So the probability that x is less than or equal to some value little x is 1 minus the CDF of little x written as a function of z. And so if we want to differentiate this with respect to x in order to obtain a PDF for, or differentiate with respect to z in order to get this. So differentiating that can be done in 2 steps. That should be an x there, typo. Anyway, the derivative of the CDF chain rule, we get a negative x squared in the denominator. And then that, if we plug into the original PDF, writing z as a function of x, we get this expression here, which we can simplify the exponents a little bit, and we get this PDF there, which is the PDF of x. Yes?
Why did that sign flip happen?
So before we were talking about increasing transformations, so the derivative was going to be positive. In this case, the reciprocal is a decreasing transformation, not necessarily linear, but my arm is linear. And so there's, you know, the inequality gets multiplied by a negative number, and so you have to flip it around. In general, a rule that always works is to take the PDF written as a function, you know, transformed into the one that you know, multiplied by the absolute value of the derivative, and then you don't have to worry about which way the sign goes, because a PDF has to be a positive function. If your PDF is ever negative, you're doing something wrong. So just multiply by the absolute value of the derivative, and you're good. Yes. Oh, yes, that's a big problem. So us in particular, and statisticians in general, are mostly concerned with one-to-one transformations and rarely anything else. But it is more complicated if you have, you know, 2 solutions to the transformation or something like that. Okay, the reason why we're doing that is because, like I said at the beginning, we're almost never doing analytical integration of a PDF to figure out the CDF. And so how are we going to get, how are we going to define these multivariate distributions? One way is with this telescopic thing, but probably a more common way, which multivariate probability distributions are derived, is by applying some transformation that induces dependence between k independent random variables that have some specified distribution. So take k random variables that are independent of each other, apply some transformation to those k variables, get k new variables, and figure out what the k distribution of the k new variables is after transforming them. And so you have to know how to do a change of variables, not just like this in the univariate case, but in the multivariate case, which is even more fun. And in order to learn about that, we have to say a little bit about a determinant. So a determinant is a scalar function of a matrix that is somewhat analogous to the absolute value operation. The absolute value operation for a scalar, if you kind of apply that to a matrix, you get a concept known as the determinant. And because it's kind of like the absolute value or the magnitude or the volume of a random variable, it's denoted with the same symbol as absolute value, you know, 2 vertical bars. But if it has a matrix in the middle, it's the determinant, which is kind of a generalization of the idea of the absolute value of a scalar. So there's formulas for how to calculate the determinant in the case of a 2x2 and a 3x3 matrix in the reading, where it's also this is for square matrices. It's also true that if the determinant is only defined for a square matrix, If the determinant of a square matrix is not 0, not exactly 0, then the inverse of that matrix exists, and the determinant of an inverse of a matrix is equal to the reciprocal of the determinant of the original matrix. And so this idea, if the determinant is not 0, then the inverse exists, is kind of a nice property in theory. So for any square matrix, it's almost surely going to have an inverse. However, when we do things in practice, if the determinant is really close to 0, but not exactly 0, then although the inverse exists, it's hard to calculate it accurately. And numerical imprecision is one of the things that could really mess Stan up, because its way of sampling is so precisely defined that if you start getting numerical imprecision in there, it can throw things off the rails. As statisticians, we're mostly going to worry about determinants of triangular matrices or symmetric matrices. For today, I think only triangular matrices. And a determinant of a triangular matrix that includes diagonal matrices, which are both upper triangular and lower triangular. Determinant of a triangular matrix is equal to the product of its diagonal entries. And so like in the QR decomposition that we were talking about last time on Tuesday, the determinant of R is just going to be the product of the diagonal elements of R. And so having a triangular matrix makes it really easy to calculate a determinant, whereas calculating the determinant for a general matrix is a pretty tedious thing to do beyond like size 2 by 2. Another important property of determinants is that the determinant of a product of square matrices is equal to the product of their determinants. And so if we have like matrix A, matrix B, multiply them together, the determinant of the product is equal to the determinant of A multiplied by the determinant of B. So what we're going to focus on today is just a case of triangular matrices. And so the determinant in that special case, it's just the product down the diagonal, right? And that's really all we're going to be using determinants for. Multivariate transformations. Here we go. So let's say Z is a random vector of size k. It has, some PDF that we know. And X is a function of Z. In particular, it's a bijective function of Z. So we have k variables. We transform them. We get k other variables. What is the PDF of the random variable X? And the PDF, possibly conditional PDF of the random variable X, is equal to the PDF of Z written as a function of X multiplied by the chain rule in the multivariate case. So if we think about this definition of the PDF, the total derivative of the CDF, and we're differentiating that first with respect to Z, and then we want to multiply by a bunch of stuff that basically gives us the partial derivatives of Z with respect to X. That bunch of stuff is sort of constitutes the multivariate chain rule, and that bunch of stuff can be collected into the determinant of a so-called Jacobian matrix. The Jacobian matrix J is a k by k matrix that contains the partial derivatives of each element of Z with respect to each element of X. So Z is indexed by the rows. So the first column of J is the partial derivative of Z1 with respect to X1. Below it, partial derivative of Z2 with respect to X1, partial derivative of ZK with respect to X1. And then over here, second column, we have partial derivative of Z1 with respect to X2, partial derivative of Z2 with respect to X2, etc. All the way down in the bottom right corner, partial derivative of ZK with respect to xk. And this square Jacobian matrix reflects the fact that if we have a vector that is a function of another vector, in general, each element of x can be a function of any of the elements of z, and vice versa, because it's a bijective function. And we're multiplying the PDF of z written as a function of x by the absolute value of the determinant. This is usually going to be a positive number anyway, but absolute value of the determinant of the Jacobian matrix. So we're going to have to stick all these k-squared derivatives into the correct place, and then somehow take the determinant of that matrix. But we're, especially today, but the rest of the semester, most of the time, we're going to cook things such that, all these over here are 0 in like the upper triangle, and thus the determinant is just going to be the product down the diagonal of the Jacobian matrix. And again, if we consider the case where k is equal to 1, so we have a vector of size 1, then the determinant of the Jacobian 1-by-1 matrix is just going to be the derivative of z written as a function of x with respect to x. And so this idea is really just a generalization of what we did previously and what we did a month or so ago in the univariate case applied to the multivariate case, a generalization for the case where k is greater than 1. So it's certainly tedious to take all these derivatives. It's even more tedious to calculate what the determinant is if you don't have a triangular matrix. But we're going to focus on the case where the Jacobians are triangular, in which case the determinant is relatively easy. Once you've figured out what all the partial derivatives are, just multiply down the diagonal. Okay, so let's see how that works a little bit in practice, although this is going to be maybe more implicit. So let's take the matrix L. This is 2 by 2. It is going to have sigma 1 in the top left, rho in the bottom left, 0 in the top right, sigma 2 times the square root of 1 minus rho squared in the bottom right. If we let z1 and z2 be independent and each standard normal, collect those into a vector of size 2 and have a corresponding vector of size 2, x1 and x2, that is a function of z, namely the function mu plus L post multiplied by z, then what's the distribution of x going to be? We can actually work this one out in more or less scalar algebra, but when we do this in the general k greater than 2 case, that's just going to be a generalization of what we have here. So the first thing we do, like we did before, is to write x, well, restating what we have here. X is a function of z. Now we're going to write this out in terms of scalars. So we've got mu1 and mu2. And then we have this matrix L post multiplied by z. Right here. And so we take z and we multiply it by the first row of L. So we have z1 times sigma 1 plus 0 times sigma 2. That's going to be the top element. And then we take z and we multiply it by the bottom row of L. We get rho times z1 plus this thing here times z2, just using the definition of product of a 2 by 2 matrix and a vector. And so if we have this x as a function of z, we can reverse this around, writing z as a function of x, where z is equal to x1 minus mu1 divided by sigma 1, and z2 is equal to this if we note that z1 here being multiplied by rho is equal to this thing here, x1 minus mu1 divided by sigma 1. So we're just proceeding like we did before. If we want x or we want to know the distribution of x when x is a function of z, we have to invert the transformation to see what z is as a function of x, and then start taking derivatives. So the Jacobian matrix in this case is just 2 by 2. Derivative of z1 with respect to x1, derivative of z2 with respect to x1, derivative of z1 with respect to x2, derivative of z2 with respect to x2. We look at this here. Derivative of z1 with respect to x1 is 1 over sigma 1. Derivative of z1 with respect to x2, z1 is not a function of x2, so the derivative over here is 0. Derivative of z2 with respect to x2 is going to be, 1 over sigma 2 divided by, or in the denominator, 1 minus rho squared. This is a triangular Jacobian matrix. Consequently, the determinant is the product down the diagonal, and so the Jacobian of this determinant of this Jacobian is 1 over sigma 1 times sigma 2 times 1 minus rho squared in the denominator. Does everybody see how I did that?
What happened to mu2?
What happened to mu2? Yes, there should be minus mu2 over there, but it's a constant, or the derivatives are not affected by that, but it's there. Drew?
What is L supposed to be?
Right now, it's a matrix. We're going to describe it more thoroughly as we go on. It's always a matrix, but I just constructed this particular matrix in order to generate the bivariate normal distribution. And so if we then evaluate the PDF of x, x1 and x2, given all these things, we take the PDF of two independent standard normals, which are z, insert z written as a function of x, and multiply by this determinant of the Jacobian matrix. And so we stick in z as a function of x here, stick in, I forgot my mu2 again, but it's also there. Stick in x, z written as a function of x there. Take sigma 1 times sigma 2 times 1 minus rho squared, break it up a little bit, put the sigma 1 over here, put the sigma 2 times 1 minus rho squared. And if I hadn't made a typo by omitting the mu2, we would have the PDF of the bivariate normal distribution that we learned before, written as a product of a marginal normal for the first one and a conditional normal for the second one, given the first one. And so we showed this in another way when we were learning the bivariate normal distribution for the first time, but it can be shown this way using linear algebra and Jacobians and determinants and stuff like that. And understanding it this way, modulo typos, is important for what we're going to do on the next slide, which is to use a similar construction to get the multivariate normal distribution in the case where k may be greater than 2. But are there any questions about this Jacobian stuff or determinants? Anything like that? In general, for a 2 by 2 matrix that's not necessarily triangular, the determinant of a 2 by 2 matrix is top left times bottom right minus top right times bottom left. And so if all the ones in the one corner of a matrix are 0, then it's just 0 multiplied by something. And so it's just top left times bottom right in this case, where we have a lower triangular Jacobian matrix. Okay, Christina. We're not conditioning on the determinant. We're multiplying by the determinant in order to get a PDF for x that integrates to 1. and consequently is a valid PDF. So if we start with a PDF for Z that integrates to 1, we do some transformation, that's going to change the area in the multivariate space under the curve. And so we have to multiply by the Jacobian, or the determinant of the Jacobian matrix, in order to counteract that and to make the area under the PDF for X equal to 1 again. So the transformation changes the area, and then multiplying by the determinant of the Jacobian matrix counteracts that change in area or in multi-dimensions volume, so that the PDF integrates to 1 again, and it's valid for probability. Okay, all that is basically to lead up to the multivariate normal distribution, which, as I said, is the most important multivariate probability distribution, both in theory and in practice. So if ZK is some standard normal random variable, it's independent of each other for all k. X is a function of Z, namely mu plus L post multiplied by Z, where L is a lower triangular matrix and its diagonal elements are strictly positive. What is the distribution of X? So if X is equal to mu plus L times Z, then Z, written as a function of X, is going to be X minus mu pre-multiplied by the inverse of L. Remembering, if we multiply, so basically we just move mu to the other side by subtracting it, multiply both sides by L inverse, we get this expression here, and then L inverse times L is the identity matrix times Z is Z. So Z, written as a function of X, is the inverse of L, multiplied by the difference between X and mu. Consequently, if we write this out in terms of scalars, the ith element of the vector Z, written as a function of X, is just going to be the vector product of some row, the ith row of L inverse, multiplied by the column vector X. But because L is a lower triangular matrix, all its upper triangular elements are 0. And so we have 0 multiplied by a bunch of stuff. So the only thing that we have to sum up to is starting from 1 and going up to element I, because all the upper triangular elements of L, where the column index is greater than I, are going to be 0. This follows from the property, which I think we said last time, but it bears repeating, that the inverse of a lower triangular matrix is also a lower triangular matrix. And so if this is an expression written out in scalars for Zi as a function of X, then we ask ourselves, what is the partial derivative of Zi with respect to xj? And we can see from this expression right here that the partial derivative of Zi with respect to xj is just going to be the ij element of L inverse. And that is true for all I and all j. Consequently, the Jacobian of the transformation from X to Z is also going to be L inverse. So L inverse contains the partial derivatives of Zi with respect to xj in its ij element. And as we said before, the upper triangular elements are all 0. So the determinant of this particular Jacobian matrix is easy because L inverse is lower triangular. It is just the product down the diagonal of L inverse. And as we said before, the determinant of an inverse of a matrix is equal to the reciprocal of the determinant of the original matrix. So we can just write this as 1 over the determinant of L, and the determinant of L is the product down the diagonal of L. So that's step 2. Step 3 is to write the PDF in terms of X. So we take our PDF for Z, write it as a function of X, multiply by the determinant of the Jacobian. We get an expression like that here. In this case, Z has a standard normal distribution. So, and they're independent of each other. So we can write this as the product from 1 to K different PDFs, but they're all standard normal PDFs. So we have this simplification here of the normal distribution. The product of a bunch of things in the exponent of E can be written pulling out the square root of 2 pi, writing it on the outside, E negative 1/2, the sum of squares of Z. That just follows from the fact that the product of a bunch of things with the same base is equal to the sum of the exponents and the base raised to that power. And since we have an expression here, sum of squares of Z, we can write that as dot products or a dot self of Z with itself. Now we're ready to substitute Z for X, where here is our expression for Z in terms of X. So we take Z and put in L inverse times X minus mu, and then we do that whole thing transposed, remembering that transposition reverses the order of a product. So we have L inverse transpose, and then multiplied on the left by X minus mu transpose, and then we have our determinant that comes from L in the denominator here. So this is one form of the multivariate normal PDF obtained by transforming up K independent standard normals. Now, this is not the form that you see most often in books, even though this is the form that is usually going to be most useful for Stan. What you see most books and stuff do, they make a further substitution, letting sigma be equal to L times L transpose, and noting the fact that this is equal to sigma inverse. And if using our rule before that the determinant of sigma is equal to the product of these two determinants are the same. So you can write that as the square root of the determinant of sigma in the denominator there. So this is the form of the PDF that you'll see most often in books when they're talking about a multivariate normal distribution. But both of these are equivalent. They're just parameterized in different ways. One in terms of L, the other in terms of L times L transpose, which is sigma. Sometimes one form or another is more useful for like theoretical purposes, but in terms of using them in Stan, what's going to be most useful is this form here, where we have X PDF conditional on its expectation mu, and this matrix L that is lower triangular and thus kind of easier to work with. So it's not like we're going to have a final exam question on those 5 steps, but it is important that you kind of understand at a high level what's being done here to define a multivariate distribution as a transformation of K independent variables. And really, basically, all of the multivariate distributions are defined this way. Start with some independent random variables from some distribution, whose PDF you know, apply a transformation that takes independent variables, makes them into dependent variables, and then figure out what the PDF of the transformation is using the simple 4 or 5 step process that we've been talking about, but generalized for the multivariate case. And so you have to worry about Jacobians and determinants rather than just doing one partial derivative in a chain rule one time. Okay, so I don't want to dwell too much on that, but that's kind of an idea of where multivariate distributions come from. So going back to Drew's question, what is L? So L is a matrix. L is lower triangular. L has strictly positive diagonal entries, and L times L transpose is equal to sigma. And so in a manner of speaking, L is kind of a square root of sigma. There's more than one way to define a matrix square root, but this is one of them. If you can take L multiplied by L transpose and get some matrix sigma, then in a manner of speaking, sigma is or the square root of sigma is L. Specifically, when done this way, L is unique, and it's known as the Cholesky factor of sigma. I think I know how to pronounce Cholesky. This one is Russian. But like a lot of Russian names, they spell it 4 or 5 different ways when it's translated into English. And so you'll see this guy's name spelled a bunch of different ways. Anyway, L is known as a Cholesky factor of sigma. There's functions to calculate a Cholesky factor in both Stan and R. It's called Cholesky decomposed in Stan. It's called Chol in R. R also confusingly outputs the transpose of L, which is the upper triangular matrix. In Stan, it's going to output L, the lower triangular matrix. You don't need to memorize this formula, but this formula is important. You can calculate the elements of L recursively from the elements of sigma. It's going to have 0 in its upper triangular, this thing on its lower triangular elements. But along the diagonal, you have the square root of the difference between the jth element of sigma and the sum of squares of all the previous elements for the corresponding row of L. And then you have to take the square root of it. So you've got a problem if this turns out to be a negative number, because you can't take the square root of a negative number and get a real thing. So we say that sigma is positive definite if all of these diagonal elements of L are guaranteed to be real, which is to say this is bigger than this sum of squares. And so if sigma satisfies that condition, we say that sigma is positive definite, and covariance matrices are positive definite. Positive definite matrices are guaranteed to have an inverse. The inverse of a covariance matrix is known as a precision matrix. Covariance matrix is symmetric, but not all symmetric matrices are positive definite. So you can't just take a bunch of numbers, stick them into a square matrix. Even if it's symmetric, it might not be positive definite. And so one way of constructing a positive definite sigma is starting by constructing L that's lower triangular and has positive diagonal elements, and then multiply L by L transpose. Now your sigma is guaranteed to be positive definite when you invert that operation. But in general, not all symmetric matrices are positive definite. This idea of positive definite or a positive definite matrix is sort of the matrix analog of a positive number. We talked about last time the identity matrix is the matrix analog of the number 1. Number 1 being a positive number. The identity matrix is also positive definite, but there's positive definite matrices that are not the identity matrix. And they can also be thought as sort of like a positive matrix. However, a matrix that has all positive numbers is not necessarily positive definite, which is kind of confusing. But we can say that one matrix, square matrix, is bigger than another if you sort of subtract one matrix for the other and you get a positive definite matrix. You can say the first matrix in some sense is bigger than the second matrix, in much the same way that we think about one positive number being bigger than a other positive number in the scalar case. And so L is Cholesky factor of covariance matrix of a multivariate normal. So just finishing out some of the properties of the multivariate normal distribution. These follow pretty easily from the linearity of the expectation operator. So the expectation of x under a multivariate normal distribution is the expectation of u plus L times z. Mu is a constant, so expectation of mu is just mu. L is a constant. We can pull it out of the expectation operator. The expectation of Z is a 0 vector. The expectation of Z is a vector of expectations of standard normals. So L times 0 is 0. Consequently, the expectation of X is mu under a multivariate normal distribution. Similarly, we can take the expectation of the outer product of X minus mu. That is equal to the expectation of L times Z transpose times L transpose. We can take the L's out because they're constant and evaluate the expectation of Z times Z transpose, where Z again consists of random variables that are independent. So they're going to be uncorrelated and standard normal. So along the diagonal of this, we have Z squared. And the expectation of Z squared, if Z is standard normal, is 1. Consequently, this matrix inside here is the identity matrix. L times the identity matrix times L transpose is just L times L transpose, or sigma. So sigma is the variance covariance matrix of X under a multivariate normal distribution. If K is 2 or K is 1, this whole thing simplifies to a bivariate or a univariate normal distribution, respectively. So it's sort of a generalization of the bivariate normal distribution that we talked about, which in turn was a generalization of the univariate normal distribution that we talked about like the 3rd week or something like that. Also, it's useful for figuring out a couple of last properties of the multivariate normal distribution to partition X into 2 pieces. So X is a vector of size K. XA is a subvector, so of size less than K. And XB is a subvector, so if you stack XA on top of XB, you get the original vector X that you started with. Do the same thing with mu, partition it at the same place. So you stack those up. With sigma, it's a variance covariance matrix, so you have to partition it once along the rows, once along the columns. So we have top left, bottom right, top right, and bottom left being the transpose of the top right piece, because sigma is a symmetric matrix. And we can also partition the Cholesky factor in much the same way. It has a top left, a bottom right, a bottom left, and the upper triangle is all 0 because Cholesky factors are lower triangular. So if we partition X and mu and sigma and L up in this way, it is relatively easy to show that X sub A, the first subvector of X here, is marginally multivariate normal itself with expectation mu A and variance covariance sigma AA. So the top left part of sigma is the variance covariance matrix of XA in isolation, and the Cholesky factor of sigma AA is just LAA. Similarly for XB, it's going to be multivariate normal with expectation mu B and variance covariance matrix sigma BB, although LBB is not the Cholesky factor of sigma BB exactly, but still XB is marginally multivariate normal itself with expectation mu B and variance covariance matrix sigma BB. Final property of the multivariate normal distribution that you have to know, XB, so this part of X, this subvector of X, conditional on XA, the top subvector of X, is also going to be multivariate normal, conditionally multivariate normal. It is going to have conditional expectation mu B times the bottom left part of the big sigma matrix, multiplied by the inverse of the top left, multiplied by the difference between X and its marginal expectation mu A. This should be XA here. I'll fix that. And then X sub B, conditional on X sub A, is conditionally multivariate normal. Here is its conditional expectation. Its conditional variance covariance matrix is sigma BB minus this multiplied by the inverse of that, multiplied by that. And this is going to be a positive definite matrix itself. You can reverse it all around, and XA conditional on XB is also going to be conditionally multivariate normal with similar expressions for the conditional mean and the conditional covariance, just switching the what do you call them? Subscripts of A and B in order to get the correct expression. So the multivariate normal, like I said, it's very important, and it has the important properties that if you have something that's joint multivariate normal, any subvector of that is going to be marginally multivariate normal. So if you take a subvector of size 2, that's going to be bivariate normal. If you take a subvector of size 1, that's univariate normal. So the marginal distributions of a joint multivariate normal distribution are themselves multivariate normal, just smaller. And also the conditional distribution of one part of X given the other part of X is also going to be a conditional multivariate normal distribution. And we know how to write down the expressions for the conditional expectation and the conditional variance covariance matrix. And so the multivariate normal distribution has this property of, you know, you can chop it up, you can condition on one or the other. Everything stays in the multivariate normal family. It's just you got to do the, you know, manipulations right to figure out what the conditional mean, conditional variance are. And that is what makes the multivariate normal distribution so useful. And the fact that these properties that we've talked about today can all be shown analytically is one of the reasons why the multivariate normal distribution is used so often. It's really difficult for other forms of multivariate distributions to be able to prove all these properties like this. And indeed, for a lot of multivariate distributions that are not based on the multivariate normal, properties like this, you know, aren't even true. So that's one of the reasons why, you know, when we pick it up next week, start using the multivariate normal distribution as a prior in a hierarchical model, it'll be relatively tractable in addition to relatively easy for Stan to sample from one of these posterior distributions. Okay, that's it for today. I will post the next homework tonight. It'll be due a week from today before class, and start the reading for next week on hierarchical models. For Tuesday, it'll be another chapter from Statistical Rethinking. It's a really good chapter, but don't get too caught up with the software that goes along with statistical rethinking to estimate hierarchical models. We won't be using that particular software, which is just another front end for Stan. Rather, we'll be using, you know, our Stan ARM and, you know, some other things later on in the semester. All right, that's it.